Have you ever looked at a perfectly natural smile and wondered what it's made of? Well, chances are the magic behind it is a material called dental porcelain. Today, we're going to break down the science behind it, all the way from its surprisingly simple origins to the high-tech wizardry of a modern dental lab. So, let's start with a little riddle. What could a teacup and a tooth possibly have in common? I know, it sounds a bit strange, but the answer is what connects an everyday object you probably have in your kitchen with some of the most advanced science in dentistry. And the answer is, they're both a type of ceramic. You know, the word itself comes from the ancient Greek word keramos, which literally just means burnt stuff. It's such a great, simple name for any material that gets its properties from being fired in a super hot oven, whether that's an old clay pot or a brand new dental crown. But, and this is a big but, while they share that name, you can't just grind up your favorite teacup and make a tooth out of it. The porcelain that goes into your mouth is a whole different beast. Really, the secret, like with any great dish, is all in the recipe. It's the specific ingredients and, more importantly, the proportions of those ingredients that make all the difference between simple pottery and a sophisticated piece of dental art. So, check out this table. It lays out the recipes for 3 different kinds of porcelain. Up top, you've got your standard decorative porcelain. Think teacups. And below that, you have 2 types used in dentistry. Just a quick look at the numbers tells you these are not the same thing. Not even close. And the most dramatic difference, the real game changer, is the amount of clay, or kaolin. Your teacup is a whopping 50% clay. But look at the dental versions. One has just 4%, and the other, the more common one, has 0. Absolutely none. So the key takeaway here is that dental porcelain is really defined by what it doesn't have. By basically engineering all of that clay out of the recipe, you create a material that has this incredible, lifelike translucency. In fact, calling it porcelain is almost a bit misleading. It's probably more accurate to call it a dental glass, because that glassy quality is exactly what lets it mimic the look of a real tooth so perfectly. So if there's little to no clay, what on earth is in this dental glass? Okay, let's meet the main building blocks that give it both its strength and its stunning looks. First, we do still have kaolin. Now, even though it's the star player in traditional pottery, making things opaque and easy to shape, in the world of dental porcelain, it's really just a background character. It's used in tiny amounts, if at all, because any more than that would block the light and totally ruin that translucent effect we're going for. Next up, we have silica. This is the backbone of the whole operation. Think of it as the strong internal framework. Its job is to provide strength and stability, making sure that crown can handle all the forces of chewing day in and day out. And finally, we get to the real magic ingredient, feldspar. This is the master binder. See, it has the lowest melting point of everything in the mix. So when you fire it in the furnace, the feldspar melts first, and it flows all around the other particles, gluing them all together into one solid, glassy piece. It's kind of like the melted cheese on a pizza that holds all the toppings together. Okay, so we've got our recipe, but how do you go from these raw minerals to a powder that a dental technician can actually work with? Well, that all happens way before it gets to the lab. The key term you need to know here is frit. Dental techs don't just get bags of silica and feldspar. Instead, they get this highly engineered, pre-cooked powder called frit. And making this frit is a whole industrial process. First, the manufacturer mixes all those raw ingredients together. Then, they fuse them at incredibly high heat. And while that mixture is still molten hot, they shatter it, often by dropping it into cold water. That shattered glass is then ground down into a super fine powder. This whole process makes sure the material is totally consistent and predictable. Now, these frit powders are generally sorted by how hot you need to get them. You've got high-fusing porcelain, which needs an unbelievable 1300 degrees Celsius to work, but the much more common type is low-fusing, which fires in a much more manageable 850 to 1100 degree range. And that's what you'll find in most dental labs today. All right, we've figured out how to build a strong, glassy material, but that's really only half the battle. How do you make that strong material actually look like a living tooth? Well, this is where pure science starts to blend with real artistry. There's a quote that just says it perfectly. Porcelain imparts a depth of color unobtainable by other materials. It's not just about painting color onto a surface. It's about building in the illusion of depth, mimicking how light plays inside a natural tooth. So how do technicians pull this off?
They have a few tricks up their sleeves. They'll add tiny amounts of different metal oxides, which act like pigments to match any tooth shade imaginable. They can also mix in other little particles to create opalescence, that sort of subtle, shimmery, blue-white glow you see on the edge of a healthy young tooth. And then comes the final touch, the glaze.
The glaze is basically a final, clear layer of glass that gets fired over the whole crown. And it does two really important things. First, it creates this perfectly smooth, non-porous surface that won't stain. And second, it acts like a final lens, boosting that translucency and giving the tooth its vital, lifelike shine. So it sounds pretty perfect, right? Porcelain is beautiful, it's safe for the body, and it can be shaped with incredible artistry. But it's not without its challenges. Like any high-performance material, there are always some trade-offs. So on the one hand, the pros are obvious. The aesthetics are just unmatched, and it's highly biocompatible. But on the other hand, that glassy structure that makes it so beautiful also makes it brittle, meaning it can chip. It also shrinks a lot when it's fired, which means technicians have to be incredibly precise. There's almost zero room for error. So in the end, dental porcelain is this material of brilliant compromises, a constant balancing act between artistic beauty and functional strength. And as new developments continue to chip away at its weaknesses, it leaves us with a really interesting question. Will this classic material just keep getting better, or will some new innovation eventually come along and take its place? Have you ever really stopped to think about what's going on inside a modern dental crown? I mean, it's easy to just see it as a simple piece of ceramic, but it's actually an incredible marvel of material science. It's designed to be both absolutely beautiful and surprisingly strong. Today, we're going to pull back the curtain and really dig into the hidden science behind that perfect smile. All right, so here's our game plan. First, we'll kick things off with how a simple powder gets transformed into a tooth. Then we'll get into the artistry, how they make it look so incredibly real. After that, we're going to uncover its biggest weakness, and believe me, it has one. And finally, we'll look at the seriously clever science they use to make it unbelievably durable. Okay, first up, this is kind of like our own little How It's Made episode. We are going right back to square one, looking at the most basic steps for creating a porcelain crown from, well, what's basically just a very specialized powder. So it all starts with a step called compaction. Now, the best way to think about this is like building a sandcastle with wet sand. You pat it, you might even vibrate it a little, all to pack those sand grains as tightly together as you possibly can. This whole process forces out any extra water and closes up the gaps between the particles. And that is absolutely crucial for cutting down on how much it shrinks later on. Then, once it's all packed, it's off to the furnace for firing. But this isn't your kitchen oven. Oh no. Modern furnaces have a really cool trick up their sleeve. They fire the porcelain under a vacuum. So why does that matter? Well, it's all about getting rid of the air that's trapped between all those tiny little particles. This one simple step drastically cuts down on the number of microscopic bubbles, what scientists call porosity, that end up inside the finished crown. And the impact of this? It is staggering. Firing under a vacuum takes those internal bubbles from making up almost 5% of the crown's volume all the way down to just 0.5%. That makes the final material way denser and, as we're about to see, a whole lot stronger. Okay, let's pause for a quick knowledge check. We know for a fact that the porcelain shrinks a lot when it gets heated up. So what's the clever workaround they use to make sure that the final crown still fits the tooth like a glove? And the answer is B. It's the platinum foil. That little piece of foil is the secret weapon. It acts as a super stable, unmoving base. So as the porcelain gets fired, it shrinks uniformly inward towards the foil. This is what preserves the perfect shape of that all-important fitting surface. After it's all done, they just peel the foil away before the crown gets cemented in place. Pretty smart, huh? So now we've got a solid shape. But how in the world does it go from being a plain block to something you literally can't tell apart from a real tooth? Well, this next part is a beautiful mix of both science and pure artistry. The real magic is in the layering. It's not just one solid color. It starts with an opaque core, which is designed to block out the color of the prepared tooth underneath. Then they add a more translucent dentin layer, and they top it all off with a highly translucent enamel layer. This layering perfectly mimics the way light travels through a natural tooth, and it's what gives it that incredibly lifelike depth. A final, shiny glaze is the cherry on top. Okay, so we've built the perfect-looking crown. It's hard, it's beautiful, but it has a hidden flaw. And this brings us to the central conflict in our story. Porcelain is inherently brittle. And here's where the trouble usually starts. And you know what? It's completely counterintuitive. You'd probably think fractures start on the chewing surface from biting down on something hard, but that's almost never the case. The vast majority of cracks actually begin from tiny, invisible flaws on the weaker, unglazed inner surface, and then they spread outward. And get this, there's this fascinating, kind of scary concept called static fatigue. This basically means the porcelain can get weaker over time all by itself, even when you're not chewing on anything. It's caused by a slow chemical reaction with the moisture in your mouth. It's like a slow-motion self-destruction that can make it way more likely to crack later on. All right, time for another key question. Now that we know cracks start from the inside and grow when the material is pulled apart, what do you think is the best way to stop them from even getting started?
The answer is C, to create compressive stress. And this is an absolutely ingenious solution. Think about it. If a crack needs tension, a pulling apart force, to open up and grow, you can fight that by putting the whole vulnerable surface into a state of permanent compression or squeezing. A crack just can't form if the material around it is constantly being pushed together.
So how in the world do you create that all-important compressive stress? Well, this is where the science gets really, really clever, using some pretty advanced techniques to forge a much stronger crown. Scientists use two main methods to pull this off. The first one is chemical, and it's called ion strengthening. Imagine taking a small book off a tightly packed shelf and then trying to shove a much larger book into its place. That pressure you'd create is exactly what's happening here. Larger potassium ions are chemically swapped for the smaller sodium ions at the surface, which squeezes the whole structure together. The second method is thermal, where they cool the outer surface so it hardens first. Then, when the still molten inside finally cools down and shrinks, it yanks on that solid outer shell, creating that same awesome compressive effect. So what does all this mean for you? Well, it means that modern crowns are incredibly resistant to breaking, both from the forces of chewing and from that slow burn degradation of static fatigue. Of course, the science can only go so far. The skill of the dentist is also absolutely critical. They have to prepare the tooth with nice, rounded internal angles to make sure they're not creating any stress points where a crack could start. From a simple powder to a high-tech, layered, and chemically strengthened restoration, the science of dental porcelain is just constantly moving forward. And it leaves us with one final thought. As these materials get smarter and stronger, are we getting close to creating a replacement that's not just as good as a natural tooth, but maybe even better?
You know, have you ever really thought about how a dental crown works? I mean, how can it possibly stand up to the crazy pressure of biting into a hard, crisp apple without just shattering into a million pieces? It honestly seems like it should be impossible, but it's not. And it's all thanks to some absolutely incredible material science. Today, we're going to unpack that science. We'll trace the journey of dental ceramics from being super fragile to the super strong materials we have today. Let's dive in. I mean, really think about that question. We're asking a material to be two things at once. It has to look beautiful and completely natural, but it also has to be unbelievably strong. It has to put up with constant grinding, chewing, and wild temperature swings from coffee to ice cream, all without getting so much as a tiny crack. For a really long time, that was a huge, seemingly impossible puzzle to solve.
So how did we pull it off? How did we go from fragile porcelain to the high-tech stuff we use now? Well, here's our roadmap. We're going to start with the big, fundamental flaw in regular old porcelain. Then, we'll see how a super clever trick with a material called alumina completely changed the game. After that, we'll look at how engineers built even tougher cores, and then we'll check out a totally different way of making these things. And finally, we'll line them all up and see who wins on the strength scoreboard.
Okay, so our story kicks off with a material that, on the surface, seemed perfect: porcelain. You could shape it, you could color it, you could make it look exactly like a natural tooth. But it had a fatal flaw, a secret weakness that made it a pretty risky bet for something like a dental crown.
The biggest problem with porcelain is that it's brittle. Think of a delicate teacup. A tiny, almost invisible crack can start, and with every single bite, that little crack can grow and spread until, bam, the whole thing just shatters. This was the #1 challenge for material scientists. How do you make something that looks as delicate as porcelain but is as tough as, well, a rock? So the solution they came up with was honestly brilliant. It was so simple. They realized they didn't have to stop cracks from forming in the first place. That was maybe impossible. They just had to stop them in their tracks before they could spread and do any real damage.
This whole process has a name. It's called crack propagation. And that windshield analogy? It's perfect. You know how it goes. A tiny rock hits your windshield. You get that little star-shaped chip. It might be fine for a day, a week, maybe even a month, but one cold morning, you come out and that tiny chip has become a giant crack running all the way across the glass. That's crack propagation, and it's exactly what scientists were fighting against in porcelain.
And this slide right here shows you exactly what I'm talking about. In the image on the left, you see the solution. That crack is spreading, it hits one of those reinforcing particles, and it stopped cold. Dead end. But look at the image on the right. In this case, the crack just goes around the particle and keeps on trucking. This shows you something absolutely crucial. The little particles you add have to be a perfect match for the material around them.
So what was this secret ingredient, this magic material that could act like a microscopic roadblock for cracks? It was a material called alumina. By mixing a fine powder of this incredibly hard stuff into the porcelain, scientists basically created a tiny obstacle course that any new crack would have to navigate.
Okay, time for a little pop quiz. Think back to that image where the crack just snuck around the particle. Why is it so important that the alumina and the porcelain are compatible? Specifically, why do they need a similar coefficient of thermal expansion? Which, by the way, is just a fancy term for how much they expand and shrink when they get hot or cold. What do you think? A, B, C, or D? I'll give you a second to think. And the correct answer is B. If they don't expand and shrink at the same rate, you create stress right at the boundary between them. Imagine gluing two things together, and when you heat them up, one gets way bigger than the other. They're going to pull apart, right? That creates tiny gaps and weak points, basically a perfect little pathway for a crack to sneak right around those alumina particles. So they have to be a perfect thermal match. It's the secret to making that bond super strong. You know, mixing in that alumina powder was a fantastic start, but it was really just the beginning. The next huge leap forward in dental ceramics came from a new idea altogether. What if instead of just mixing stuff in, you could build a super strong internal core for the crown and then just cover that core with a layer of pretty porcelain? That way you'd get the best of both worlds, incredible strength on the inside and perfect looks on the outside. This led to something called the sintered alumina core. Here's the play-by-play. First, you make a plaster copy of the tooth, easy enough. Then you paint that copy with a watery paste of alumina powder, called a slip. Now, here comes the magic step, sintering. This is just a fancy word for baking it at a really high temperature. This fuses all the little alumina particles together, creating a structure that's strong, but also porous, kind of like a hard sponge. And for the final step, you infiltrate that sponge with molten glass, which fills in all the tiny gaps and creates a solid, incredibly strong core. And this core idea just blew the doors wide open for new innovations. For instance, they developed spinel-based cores that were way more translucent, which looked more natural. The catch? They weren't quite as strong. On the flip side, they started adding another material, zirconia, to the alumina core, which made it even stronger. But that made it more opaque, which isn't great for front teeth where looks are everything. It's this constant balancing act between strength and beauty.
But get this, while all of that work was happening on reinforcing porcelain with cores and particles, a totally different group of people was developing a completely different approach. Their method didn't rely on adding anything. Instead, it was all about shaping the material in a brand new way.
Their big idea was, what if you could treat ceramic like plastic? They figured out a way to heat the ceramic until it got soft, and then inject it into a mold, creating a perfectly precise shape. It's a bit like the ancient lost wax technique used to make jewelry and statues. The result was a crown that fit so perfectly it barely needed any adjustment.
One of the most famous systems using this method is called IPS Empress. What it does is press a special kind of molten glass into a mold. But the real genius is what happens as that glass starts to cool down. Tiny, super strong crystals of a material called lucite actually form inside the glass, reinforcing the whole structure from within. It's like having a reinforcement system that builds itself. How cool is that?
Okay, so we've seen two main paths of innovation here. Reinforcing with particles and cores on one side, and molding with self-forming crystals on the other. But how do they all compare? Which one is the real heavyweight champion? Let's check the scoreboard.
All right, let's start with our baseline unreinforced porcelain. Its flexural strength is about 80 megapascals, or MPa. Now watch what happens when we just add those alumina crack stoppers. Boom. The strength jumps up to over 110 MPa. That's a really nice improvement for sure, but we're just getting warmed up.
Now you might want to sit down for this. That centered alumina core, the one that's baked and then filled with glass, it clocks in at up to 600 MPa. That is a massive leap in durability. We're talking about a completely different league of toughness.
And here it is, the whole picture. As you can see, the numbers just keep climbing. Adding zirconia to that centered alumina core gets us to 800 MPa. And the current king of the hill, a wild material called yttrium tetragonal zirconia polycrystals, can reach up to 1200 MPa. That is more than 10 times stronger than the porcelain we started with. It's just an amazing story of scientific progress.
So there you have it. We went from a beautiful but fragile glass to a material that is tough enough for the most demanding job in the human body, all while looking totally natural. It really makes you wonder, doesn't it? What other impossible materials out there are just one clever breakthrough away from changing our world?
Hey, have you ever really thought about how a dentist rebuilds a tooth? I mean, it's way more than just a filling. We're talking about a custom-engineered cap, a tiny little helmet that's designed to take an absolute beating. Today, we're going to trace the incredible journey of the dental crown, from a process that was basically old-school sculpting to one that uses robots and, get this, self-healing ceramic.
So let's just start with the main problem, right? How in the world do you build a new tooth surface completely from scratch? One that can handle the force of chewing on a tough steak, fits so perfectly that even dental floss can't tell it's there, and looks so natural that nobody has a clue it's not the tooth you were born with? It's a huge engineering challenge, just on a super, super tiny scale. All right, here's our game plan. First, we'll figure out what actually makes a crown perfect. Then, we'll dive into the classic hands-on artist's method, which is called casting. After that, we're going to jump straight into the modern age with a digital sculptor, CAD/CAM. We'll also get into the super strength materials that make all this possible. And finally, we'll see how the whole thing comes together. So what is a perfect dental crown? Well, you can think of it as hitting a trifecta of challenges. First, it has to have incredible strength, to handle years and years of grinding and chewing. Second, the fit needs to be absolutely perfectly precise. We're talking differences measured in micrometers. And third, it has to look beautiful, a perfect cosmetic match. Getting all three of those right, that's kind of the holy grail of this whole field. Okay, let's take a little step back in time. Before we had all these digital scanners and robots, making a crown was pure hands-on artistry. Dentists actually borrowed this really clever technique from ancient jewelers and sculptors called the lost wax method. And believe me, this was about as hands-on as you can get. The whole process is kind of like a really high-stakes baking recipe. First, a skilled technician carves a perfect little replica of the crown out of wax. Then, that wax pattern gets encased in a special mold material. Next, it goes into a furnace that's heated to a blistering 950 degrees Celsius that completely vaporizes the wax, leaving a perfect hollow tooth shape behind. Then, and this is wild, molten ceramic is spun into that mold at an even hotter 1350 degrees. And finally, it goes through one last special heat treatment. Now here's where the real magic happens. It's a process called ceramic. See, the crown starts out as basically a piece of clear, pretty fragile glass. To make it tough enough to be a tooth, it gets baked at over 1,000 degrees Celsius for 10 solid hours. And this isn't just baking, it's a total transformation. That intense heat forces this whole network of microscopic crystals to grow inside the glass, turning it from something that would shatter in a second into a really strong tooth-colored ceramic. This step is the secret to the whole thing's strength. Okay, time for a little pop quiz to see if you're with me. What is the main purpose of that ceramic process we just talked about? Is it A, to color the crown, B, to increase the crown's strength, C, to melt the ceramic, or D, to clean the wax mold? So for a long time, the lost wax method was fantastic. I mean, it created really accurately fitting crowns that were even strong enough for your back teeth. But there were some downsides. It took a lot of specialized equipment, and the color was just a super thin layer painted on the surface. So if the dentist had to adjust the fit at all, they could easily grind that color right off, which obviously isn't great. And this is what really opened the door for a brand new approach. And that new approach was a complete revolution. Enter
CAD/CAM technology. We are officially leaving the artist's workshop and stepping into the digital age. This is where wax gets replaced by pixels, and those big casting furnaces get replaced by robotic milling machines. It's a whole new world.
So what exactly is CAD/CAM? Well, it stands for Computer-Aided Design and Computer-Aided Manufacture. To put it simply, you use a computer to design a perfect 3D model of the crown. That's the CAD part. Then, you just send that design to a machine that automatically carves it out of a solid block of ceramic. And that's the CAM part. It's seriously like having a tiny, incredibly precise little robot sculptor right there in the office. And this picture shows the whole setup perfectly. Over on the right, you've got the control unit, the computer, where the dentist or a technician can design the crown right on the screen. And on the left, that's the milling machine, our little robotic sculptor. This entire system can sit right there in the dental office, just ready to go, ready to create a crown pretty much on the spot.
The whole workflow is just incredibly efficient. Step 1 is the scan. Instead of that gooey tray of impression material, a tiny camera takes a digital 3D picture of your tooth. Step 2 is design. The dentist uses special software to design the perfect crown, which usually takes about, say, 10 to 25 minutes. And then, step 3, mill. The design gets sent to the milling machine, which carves the crown out of a ceramic block in just 5 to 10 minutes. It's just astonishingly fast.
And here you can get a closer look at the magic as it's happening. On the left, you can actually see the milling machine's tiny little drills or burrs precisely carving away at the ceramic. And on the right, you see what it starts with, just a solid, pre-made block of high-tech ceramic. The machine takes that blank little block and sculpts it into a perfectly shaped, custom-fit crown. It's amazing.
All right, another quick check-in for you. We know the CAD is computer-aided design, but what does the CAM in CAD/CAM stand for? Is it A, computer-aided measurement, B, ceramic-assisted milling, C, computer-aided manufacture, or D, crown adjustment machine? And the answer is C, computer-aided manufacture. That's the part where the machine actually makes the thing.
So we've seen this incredible process, but what are these crowns actually made of? Because the technology is only as good as the materials that it's using, and this is where some truly mind-blowing material science comes into the picture. Now, the tech is amazing, but the material itself is the real star of the show here. It's called yttrium tetragonal zirconia polycrystals. Yeah, I know. Or we can just call it YTZP for short. It sounds like something straight out of a spaceship, and honestly, it's not that far off. This is not your grandma's porcelain teacup. This is a super ceramic, engineered for incredible toughness. So what really matters is its strength. Just how strong are we talking? Well, YTZP has a flexural strength of between 900 and 1200 megapascals. Now, to put that into perspective for you, that is significantly stronger than a lot of metals. So what that means for you is that your crown is way, way less likely to chip or crack, even if you bite into something unexpectedly hard. But here's the absolute coolest part. ETZP has a superpower called transformation toughening. If a tiny little crack starts to form, the ceramic crystals right at the very tip of that crack instantly change their shape. They expand, creating this compression zone that literally squeezes the crack shut and stops it from spreading any further. It's like the material is actively fighting back to heal itself. How cool is that? Okay, so we've got our super strong, robotically sculpted crown. We are almost at the finish line. Now we just need to attach it to the tooth. But this final stage actually reveals what might just be the one remaining challenge in this entire process. So these last steps are all about creating a super strong bond. First, the inside surface of the crown is chemically etched to make it kind of rough and grippy. Then a special primer, it's called a Porcelain coupling agent, is applied. You can think of it like a piece of double-sided sticky tape between the ceramic and the glue. And finally, the crown is bonded to the tooth with a special dental cement called a resin lute. But here is the catch. Just look at this comparison. The ceramic crown itself has a hardness value of over 300, but the resin cement, the lute that's holding it in place, its hardness is only about 20. That is a massive, massive difference. So we have this superhero crown being held in place by a much, much softer material, and this introduces a potential weak link in the chain. So what does that actually mean in the real world? Well, over time, that much softer cement can slowly wear away right at the edges of the crown, and that creates a tiny gap or defect. This is exactly why the incredible accuracy of CAD/CAM milling is so important. A better, tighter fit means a smaller gap, which means less exposed cement, and that all adds up to a stronger, longer-lasting restoration.
And that brings us to our final question. We've gone on this journey from hand-sculpted art all the way to robotic manufacturing, from simple glass to self-healing ceramics. But that final weak link, the cement, it's still there. So what's the next big leap forward? Is it going to be a new kind of biological glue, or maybe a crown that can actually fuse directly to the tooth? The quest for the truly permanent restoration, well, it continues.
Welcome to The Explainer. Today we are diving deep into the science behind that perfect Hollywood smile. And spoiler alert, it's not just about good brushing. It's about some incredible material science, specifically something called a porcelain veneer. We're going to find out how a piece of ceramic thinner than a fingernail can totally change a smile, and why it's way, way stronger than you'd think.
I mean, you've seen them, right? Those celebrity smiles with teeth that are perfectly white, perfectly shaped, and you've got to wonder, how in the world do they get that way? Well, the answer usually isn't just good luck or whitening toothpaste. It's a really cool mix of material science and chemistry, and we're about to unpack exactly how it all comes together.
Okay, so let's start at square one. Before we get into all the crazy chemistry and physics, let's answer the most basic question. What is a porcelain veneer?
Just think of it like this. It's a custom-made, super thin shell made of ceramic. It's not a full crown that covers the whole tooth. Nope. It's more like a delicate new face that gets bonded right onto the front of your tooth to completely change how it looks. It's like cosmetic surgery for a tooth, but on a totally microscopic level.
Now, right off the bat, there's a big debate in the process. Do you stick the veneer right on the tooth as is, or do you prepare it first? Well, most experts say you get a much better fit if you remove a tiny, tiny bit of enamel first. We're talking about 0.5 millimeter. That is literally thinner than a credit card. It might sound a little scary, but it's the key to making sure the veneer sits perfectly flush and doesn't look bulky.
All right, so once the tooth is prepped, the spotlight turns to actually making the veneer. And this is not an off-the-shelf kind of deal. Every single one is a custom piece of engineering designed from scratch.
And this is where things get really high-tech. The veneer itself is barely 0.5 millimeter thick, which is just wild. And they're made from these advanced ceramics. Some are carefully layered and baked by hand, kind of like fine china. Others are pressed from a solid block of super strong glass, and some are even designed on a computer and then milled out by a robot using what's called CAD/CAM technology. But no matter how they're made, the goal is always the same: create something that's both incredibly thin and unbelievably strong.
So this brings up a huge problem. The veneer is a little see-through, right? So the final color you see isn't just the color of the ceramic. It's a combination of the veneer plus the bonding agent, the glue, and the color of the actual tooth underneath. With all those layers, how could you ever predict what the final shade is going to be?
Well, it turns out they do little dress rehearsal. You could just use a drop of water to stick it on for a quick peek, but the pro move is way smarter. They use these special trial pastes that are water-soluble. These pastes come in shades that perfectly match the final cement, so you get an exact preview of the final result. And the best part? If the color's not quite right, you just rinse it off and try a different shade. Zero guesswork involved.
So, we have the perfect shape, we've nailed the perfect color. Now for the main event, making it stick forever. And this is where the real science comes out to play. We are not talking about Elmer's glue here. This is a hardcore, multi-step chemical process that creates a bond designed to last for years and years.
The entire thing really comes down to 4 crucial steps. It's kind of like a chemical recipe. You have to prepare both surfaces, then you add a special matchmaker molecule to connect them, and finally, you lock it all in place. You have to do every single step perfectly. So let's break them down. First up, you have to etch the tooth. A mild acid gel is put on the enamel for just a moment. It sounds intense, but it doesn't hurt the tooth at all. What it does do is create millions of microscopic little pits and pores on the surface. Imagine turning a smooth piece of glass into frosted glass. You're basically creating tons of little nooks and crannies for the bonding agent to grab onto.
Next, step 2. And you can probably guess what it is. You do the exact same thing, but this time to the inside surface of the veneer. They use a different kind of acid that's made for ceramic, but the principle is identical. Create that same microscopic rough texture. So now you have 2 perfectly prepped surfaces just waiting to be joined together.
And now for the real magic trick. See, you're trying to glue an inorganic thing, the ceramic, to an organic thing, which is the resin. And chemically, they just don't want to stick to each other. So you need a go-between.
That's where this stuff called a silane coupling agent comes in. The easiest way to think of it is like double-sided chemical tape. One side of the molecule is designed to grab onto ceramic, and the other side is designed to grab onto resin. It's the essential handshake that makes the whole bond possible.
And finally, step 4, the grand finale. A special resin cement is put on the tooth, the veneer is pressed into place, and then a special blue light is used to harden the resin and lock everything together for good. And the fact that it's activated by light is super important. It means the dentist has plenty of time to wiggle the veneer around, get the position absolutely perfect, and only then, bam, they hit the light and make it permanent.
Whew, okay. That was a lot of chemistry, I know. But were you paying attention to that crucial middle step? Let's do a quick quiz and find out.
So the question is, what's that special agent that acts as the chemical go-between, connecting the ceramic veneer to the resin? Is it A, B, C, or D? I'll give you a second. If you were thinking about that double-sided chemical tape, then you got it. The answer is C, the silane coupling agent. That's the secret sauce molecule that makes this whole thing work.
All right, we're on to our final section, and we're going to tackle the biggest head-scratcher of them all. How can something so thin, and technically so brittle, be so unbelievably strong when it's in your mouth? I mean, seriously, think about it. You're bonding a thin, rigid, fragile piece of ceramic, basically glass, onto a tooth which has a bit more flex. Common sense tells you that the first time you bite into a crunchy apple, that veneer should just snap, right? But it doesn't. So what is going on here?
The answer comes down to a really cool concept called critical strain. Basically, any ceramic material will break if you bend or stretch it more than a tiny, tiny amount. We're talking just 1/10 of 1%. But the genius of the veneer system is that the bond is so complete, so perfect, that the veneer and the tooth act like one single object. So when you chew, the force goes right through the veneer and gets spread out across the entire, much stronger tooth. The veneer itself never gets stressed enough to reach that 0.1% breaking point. It's completely protected by the tooth it's attached to.
So this incredibly clever multi-step process is what makes porcelain veneer so amazing. But you might be wondering, are there any simpler options? Well, yes, but as you're about to see, they come with some pretty big trade-offs.
So for instance, you could use a composite resin, where the material is kind of sculpted right there on your tooth. Or you could even use pre-made acrylic veneers. But just look at the chart. When it comes to durability, nothing even comes close to porcelain. So yeah, the porcelain technique is definitely more complex and takes more time, but the payoff is a result that's way more resilient and is built to last.
And this all brings us back to a really great quote from the source material, which says that the clinical success of porcelain veneers is, and I'm quoting here, surprising. I love that. It's basically the experts admitting that, on paper, it seems like it shouldn't work as well as it does. It's just a true marvel of science.
So let's boil it all down one last time. What are the big takeaways? First, veneers are ultra-thin ceramic shells that make teeth look better. Second, the real secret is that sophisticated multi-step chemical bonding process. And third, they're so surprisingly strong because that bond lets the tooth take all the pressure, keeping the veneer safe and sound well below its breaking point.
And that leaves us with a final thought to chew on. What other things in our daily lives are seemingly fragile, but are made incredibly strong simply because of how they're supported and bonded to something else? Once you start looking for it, you'll start to see this principle pop up everywhere.
All right, let's dive into a true classic of restorative dentistry, the porcelain fused to metal crown. You might hear it called a PFM for short. Now, this isn't just a piece of technology. It's a really clever solution that combines the best of two totally different worlds. So what you're seeing right here, that's the finished product. On the outside, it looks just like a natural tooth, right? Beautiful, tooth-colored porcelain. But what you can't see is its secret weapon, a super strong metal core hiding underneath. And that hybrid design, well, that's the key to the whole thing. And really, that brings us to the core problem that dentists were trying to solve for ages. Think about it. You need a replacement tooth to be tough enough to handle all the force from chewing day in and day out, but at the same time, it has to look good. It has to blend in with a person's smile. So how on earth do you get both strength and beauty in one single package? Well, you probably guessed it, the answer is the PFM restoration. This is so much more than just slapping a layer of porcelain onto some metal. It's a really elegant bit of material science, designed from the ground up to solve that exact problem. You know, I absolutely love this quote from our source. The word marrying is just perfect. It's not about one material being better than the other, it's a true partnership. The metal brings the muscle, that mechanical backbone, while the porcelain provides the beautiful, natural-looking exterior.
Okay, so how does this marriage actually work on a technical level? Well, to figure that out, we gotta pop the hood and deconstruct the crown. Look at its blueprint. Let's start with the foundation itself, that metal core. See? This metal substructure isn't just any old piece of metal. It has 4 incredibly important jobs to do. First, it has to have really high heat resistance. Why? Because the porcelain is literally fired onto it in a super hot oven, and the metal can't melt or warp. Second, it has to be super rigid. Porcelain is basically a type of glass, so it's brittle. If that metal base flexes even a little bit, the porcelain will just crack. Third, it absolutely must be able to form a rock-solid bond with a porcelain. And last, but definitely not least, is thermal compatibility. This means the metal and porcelain have to expand and shrink at almost the exact same rate when they get hot or cold. If they don't, that stress would just pop the porcelain right off. So, getting that thermal expansion just right is absolutely critical. And on the porcelain side of the equation, the secret ingredient is a special crystal called lucite. This stuff is genius. It's mixed into the porcelain for 2 big reasons. 1, it increases the porcelain's expansion rate so it perfectly matches the metal. And 2, as a really nice bonus, it actually makes the whole ceramic layer stronger. Pretty clever, right?
But what about that bond? I mean, how do you get glass to stick to metal so tightly? Well, the trick is something called an oxide layer. You see, they add tiny amounts of metals like tin or indium into the alloy. When the crown is heated up, these little guys rush to the surface and form a microscopic layer of oxide. That layer acts like a chemical handshake, a bridge that allows the porcelain to form a true, powerful chemical bond during firing. It's this invisible little layer that holds the entire restoration together.
So now that we know what the metal needs to do, let's look at the actual metals they use. There are basically 4 main families of alloys that have been cooked up for PFM crowns, and each one has its own personality, its own set of pros and cons.
First up, we have the original, the classic, high gold alloys. And just like the name says, these guys are mostly made of gold. Take a look at this. It's like a recipe. You've got about 85% gold, but look at the other ingredients. They add things like platinum or palladium to make it melt at a higher temperature, which is crucial. And there they are, our friends tin and indidium, just waiting to create that all-important bonding layer.
So why go with high gold? Well, the pros are pretty big. Gold alloys are super easy to work with, so you get a really precise fit. Plus, they're very biocompatible, meaning the body's tissues tolerate them extremely well. But there's a flip side. They're not as rigid, so the metal core has to be a bit thicker. And because their melting range is a little lower, there's a risk the metal can actually sag or deform a bit during the high-heat porcelain fire.
Of course, gold is expensive, so naturally the next step was to find more budget-friendly options. And that's where low gold alloys come in, cutting that gold content down to around 50%. So what they do is swap out some of that pricey gold for more palladium. This actually gives them a couple of key advantages. First, it raises the melting range, so they're much better at resisting that sagging we talked about. And second, it makes them a little more rigid. This mix of really good properties and a lower price tag has made them a super popular choice for years.
But what if you wanted to take the cost savings even further? Well, the next step was to get rid of the gold completely. And that brings us to alloys made from a mix of silver and palladium. Mechanically, these are really solid. They're even more rigid and have a higher melting point than the high gold options. And the cost savings, obviously, are a huge plus. But there's one potential catch, and it's an aesthetic one. Sometimes, the silver in the alloy can cause a faint greenish tint in some types of porcelain. It's an effect they call silver greening. And that brings us to our final category, the base metal alloys. These are typically made of nickel and chromium, and they are a whole different beast compared to the precious metal options. So the big pro here is pure muscle. Nickel-chromium alloys are incredibly rigid and have a super high melting temperature. But, and these are pretty big buts, the trade-offs are significant. They can be tricky to cast accurately, and their bond to porcelain isn't quite as tough. A failure is more likely to happen right at that oxide layer. On top of that, some patients can have sensitivity or allergy issues with nickel. So we've got these 4 very different families of alloys. And honestly, the best way to wrap your head around them is to see them compared side by side, looking at the properties that really matter. Okay, now this table tells the whole story. It just lays out all the trade-offs so clearly.
Check out castability, how easy it is to work with. High gold is excellent. Nickel chromium is poor. But now look at modulus. That's the rigidity or strength. The roles are totally flipped. Nickel chromium is the toughest. And then you get to biocompatibility, where high gold shines again and nickel chromium can be a concern. This really shows that there's no single best alloy. The choice is always a balancing act between cost, strength, looks, and what's right for the patient. Now, while those four are the big players, science never stands still. People are always looking for new and better ways to do things. So let's just quickly touch on a couple of alternative ways to make that metal core. One really neat method is called capillary technology. It basically builds the core from a delicate metal mesh and then infuses it with molten gold. Another one is bonded platinum foil, where the porcelain is bonded to a really, really thin sheet of tin-plated platinum. Now, it's not as strong as a traditional cast core, but its big advantage is that you don't have to remove as much of the healthy tooth to make it fit. And that's always a huge win in dentistry. So when you boil it all down, the big takeaway is this. The porcelain fused to metal crown is a masterful balancing act. It's a technology born from a really deep understanding of metals, ceramics, and some pretty slick chemistry. It's all about finding two materials that are compatible, and then creating the perfect environment for them to form a bond that can survive inside the human mouth, which is one of the toughest environments imaginable. And that kind of leaves us with a final question to chew on. PFM was the great material marriage of its time, but today we're seeing these amazing advances in all ceramic crowns and other new materials. It really makes you wonder, what's next? What will be the next brilliant hybrid? The next ingenious pairing of materials that's going to push dentistry even further?